Hello everyone, we're going to be solving a physics problem for geometric optics, and this is going to be a problem about Snell's Law. So the problem says a narrow beam of light containing red 660 nanometer and a blue 470 nanometer wavelengths travels from air through a 1.0 centimeter thick flat piece of crown glass and back to the air again. The beam strikes at a 30-degree incident angle. At what angles do the two colors emerge, and by what distance are the red and blue lights separated for when they emerge? Okay, so to solve these types of problems, you're going to want to use Snell's Law. Okay, so n1 of sine theta 1 equals n2 sine theta 2, right? And then usually when you start these problems, one thing I want to note, if you've never done any of these kind of problems before, the ends, right, are considered the index of refraction. So N1 is the medium 1, which is the air, and N2 is going to be the glass. And there's always the incident angle, and theta 2 is the angle of refraction. So just keep that in mind when you're whenever you're setting up these kind of problems. And whenever you start these problems, the first thing you want to do also is you're going to want to draw a diagram. So let's get started with the diagram. Let me just label it. Right? So we're going to start by using some information from the table or from the problem. It said it was a 1.0 centimeter thick piece of glass, right? We're going to call this side over here N1. This is going to be N2. And since it comes out on the other side, as it said in the problem, we're going to call that N3. So how am I going to draw this? Well, the first thing I'm going to do is I'm going to draw the beam of light coming in, right? Let me give this a little more room so I could draw a little better. Okay. So this is going to come in. Let's say a beam of light is going to come in from, let's just say, this direction. Then it's going to go through, kind of slightly bend like a little bit. And then it's going to bend back up this direction. Right? Now, if you notice that we said that it was going to bend and produce two different kinds of wavelengths. So we're going to call this bend, we're going to denote this as the blue light is going to bend right here. Right? And then it's going to go and bend up this direction. Okay? Let's see if I can use my red pen to redraw this one as red, so it's a little more clear. So we know that this is the red light, right? Now, we said from the problem that the thickness of the glass, the crown glass specifically, is 1.00 centimeters, or we're just going to call it 0.01 meters, because we're going to need that information later. We're just going to call that one X, right? Now, we said that the incident angle is going to come in at 30 degrees, so what we're going to do is we're going to draw a normal line from here, like this, and we're just going to go ahead and draw it all the way across the glass. You never know what we might need, right? And then we know that their incident angle is theta 1, right? And we're going to label this as 30 degrees. Now, since we're dealing with multiple different angles here, we're going to have to denote these specifically. So this is going to be, this angle of refraction here is going to be theta 2. And then we're going to call this other angle here theta prime of 2. So we might need that information later. And then a third angle, you know what, I should draw another normal line because everything's refracting here. Draw another normal line there. Then we're going to draw another normal line here. Because we're trying to find distance. So when we're calculating the distance they're apart, we're going to probably need some information from them. So we're going to call this distance, the first distance anyway, we're going to call this one y prime, and then the whole distance, because we want to know how far it bent away from it originally coming in, right? We're just going to call that y. Now that we got some more of this information set up, we're going to have to denote some stuff a little better here. So this angle right here, and then this angle, we're going to call this one theta 3, and we're going to call this one theta prime of 3. Okay, that looks like a pretty good diagram so far. Now that we got a diagram, we can kind of start entering some information, but first we got to look at a table to get some of the n values, because I don't know offhand what crown glass is or how thick it is, so I got to look at this table. So if you go to a table, it tells you, we're going to write that down from a table. You're going to put N2 is 1.512, and then the N prime of 2 equals 1.524. And the reason why it's slightly different is because recall that we're talking about two different wavelengths, the red and the blue wavelength. And we're using medium crown glass. So now that recall that we wrote down our equation, right? The N1 equals sine theta 1, N2 equals sine theta 2. But that same expression, since we're dealing with multiple transitioning surfaces, it's also going to be the same as N. It's going to equal, N3 sine theta 3, right? So, knowing that, we know that N1 sine theta 1 is the same as this. But we're just going to restate it just because. Now, from our table also, if you don't know, the N value for air is just going to be used as 1.00 for this problem. I know that's typically what it is in a vacuum. Think air is like 1.00029, the exact value. But for our purposes, we don't really need that. Now, if you look at the information above in here, you're going to see that N1 is equal, like all these expressions are like equivalent or equal. So we can start getting started to trying to solve the problem. But let's think about for a second, what are we going to solve here? There's different mediums that it's going through. So we also need to note that N1 sine theta 1 is equal to N prime of 2 sine prime, or sine of prime theta 2. And that is also going to be equal to N3 sine theta prime of 3. So if you look back at the diagram, we have all these different angles that we're dealing with. So we want to try to be as thorough as possible when trying to solve for what we're looking for. And then we're going to note too that N1 equals N3 in all cases. So this information that I put specifically, we're going to try to use this to solve for the blue wavelength. Okay. So if we're solving for the blue wavelength, we got to solve for the red too, right? But we're going to get to that in just a minute. We're going to go back to the first part of the problem when it's asking. The first part of the problem, it asks what angles do the lights or the rays of light emerge. So we're going to go ahead and note this down. For part A. This is part A. Where do they emerge? So, to find out where they emerge, you're going to just look at the given information. N sine theta 1 equals N1 sine theta prime 3. So we know that theta 1 is the same as theta prime of 3. So you have it over here. So those two are equal using Snell's law. And we also know that theta 3 equals the same as theta prime of 3, which is the same as theta 1. Did you look at that? So if they're all equal, wouldn't they all be 30 degrees? Right? So that's the angle which they emerge. Forgot a question mark there. Got to be grammatically correct too. Now, let's get the angle of refraction for the red light. Let me change color here so I know I'm working for the red light. Okay? So we're going to manipulate our Snell's Law equation. We're going to solve equals the inverse sine of N1 sine theta 1 over N sub 2. Now, all this information we have either from the problem or from the table. Since we solved for the incident angle from the previous one, even though it's given if we needed to solve for something else, but it's kind of good that it's all there. So we're going to finish solving the problem equals the inverse sine, and we're going to plug in this value. Times the sine of 30 degrees over the N2, which we got from our table, and if you plug that into the calculator, you're going to get 19.311 degrees. Now, we're going to have, now to solve for the blue light, let me get a different pen. We're going to rearrange the equation again for the blue light. Okay, so theta prime of 2 equals the inverse sine of N1 sine theta 1 over N prime of 2, right? Since we're calling it prime because of the different wavelengths, in case I forgot to mention that. Now we're going to fill it in. substituting our values from before, over the n prime 2 value for the blue wavelength. And you're going to get a number close, but not exactly the same. We still want to keep the correct amount of significant digits. Now, let's go back to our diagram really quick and look at some information because we're solving for the distance. Now, if you notice that we got these distances here, and we're going to have to use a little bit of trigonometry, specifically the tangent, to solve for the rest. So, actually, I'm just going to use a whole new piece of paper. So, let me write this down so I know where I got the information when I continue. From the diagram. Okay? From the diagram, we're going to use trigonometry. Tangent of theta 2 equals y over x. Some people like to use SOHCAHTOA to remember trigonometry. It doesn't really matter. But we're going to rearrange this equation because we're going to try to solve for y. Because we have it on our diagram, but we don't know what the values are. And remember in the beginning of the problem that I converted it automatically, the centimeters to meters, because we're going to need to know that to be able to solve for the distance. Because distance is usually done in meters, so we're going to do it as such. So 0.01 meters equals x. And then we're going to substitute in the values to find the distance for the bigger y, which is this y right here. So we're going to go y equals 0.01 meters times the tangent. And we're going to use the information from the red ray of light first. And if you plug this into the calculator, you're going to get 3.504 times 10 to the negative 3 meters. So that's the big distance, the bigger distance right here for the total angle of the red, where the distance of how it's refracting. So now we need to try to solve for y prime to get the smaller value. So what we're going to do is we're going to use the information from the blue wavelength to do this. So let me just note this down as red. This is going to be blue. So we're going to use the same equation, but we're going to call this one tangent theta prime of 2 equals y prime over x. And then, like I said, like how we rearranged the last one, to be able to solve for it. Now, let's substitute in our values. And remember, we got this value from the blue, the work on the blue problem we did earlier. So, if you plug this into the calculator, it's going to be 3.473 times 10 to the negative 3 meters. Now, how do you get the distance between those two? Well, that's actually pretty simple. If you look at them, you're just going to subtract to get the change of y, right? The change of y is going to be y minus y prime. So if you take this and you plug in the values, the change of y equals 3.504 times 10 to the negative 3 meters. Subtract 3.473 times 10 to the negative 3 meters. You're going to get 3.1 times 10 to the negative 5 meters. This is the distance blue and red when they emerge other side. Well, I hope this problem was informative, and I hope it helps you.